All right, so today we're going to do a couple of things. So first, what we're going to do is we are going to review transformations. The second thing we're going to do is review a change of basis. And those will kind of feel simultaneously. But three, most importantly, what we're going to do is link all of this to similarity, and therefore also to eigenvectors. So transformations was really kind of like chapter, maybe even chapter 1 or 2. Change of basis was definitely chapter 4, but then similarities was kind of what we just learned in chapter 5. And so we're going to tie all of these things in together. So this last part, our goal, is only going to come in at the end. But let's review some things first. So first, any linear transformation, one, please note, has to be implemented by left multiplication by a matrix A. And this transformation can be anything. It can be rotating, it could be scaling, anything. But let's say we're starting with a vector x, an input in a certain vector space. Okay, that could be any vector space. If we want to transform that vector into a new vector space, and remember these might not be the same dimensions, you would multiply x by a and get an image, a new image of x. Usually this is where we've done all of our theoretical things about things being onto, the invertible matrix theorem, all that jazz, is dealing with the equation ax equals b. Again, we're thinking about ax as some kind of transformation. And usually, remember, one important thing is that a transformation, okay, the vector that comes in, the vector that gets multiplied by the matrix, has to have the same number of columns. So the transformation starts in Rn, and the result gets mapped to B has the same number of rows as the matrix, so it gets mapped to Rm. Okay, so that's what we have. These might not be in the same dimension here, V and W. Now, in chapter 4, what we talked about was changing the basis. So it might be that these vector spaces are currently in the standard basis, but if I want to describe V, a vector space, using a different basis, I then get new coordinates. We say that that's x with respect to the basis b. Okay? And if I map to a different vector space, it may have a different basis. And I can make that transformation too. Remember that a basis for a system is often not unique. There are multiple representations for a basis. Okay, and so today what we are going to do is we would like to close this loop. How can we go from one basis to another basis in two different vector spaces and achieve the transformation at the same time? Okay, so today we're trying to close the loop. Okay, using both our goal number 1 and number 2 was to review transformations and review the change of basis. See how we can do this at the same time. All right, now, in order to do this, we need to remember, 1, we're going between two different vector spaces, V and W. Okay, T is going to be any linear transformation between the two, and each V and W is being described by two different bases. All right, so let's look at how we might do this using some of our prior knowledge. So here's kind of a two-dimensional image of what we were just talking about. Starting with an input vector, transforming by multiplying by a matrix A, and achieving an image of x in a new vector space. And here we have basis B and basis C. So when we wanted to change bases before, what we did was we actually rewrote all of the basis vectors. So we rewrote the vectors for basis B in terms of basis C and called that the transformation matrix in between the change of basis or the change of coordinates matrix. What we would like to do now is take vectors that are described in terms of basis B and transform them by putting them through, by multiplying them by the matrix A, and then have the result be a vector described in terms of the basis C here. So this is now within basis C. So we're going to do this with all of our basis vectors for B, change them into something with respect to C, and transform them at the same time. So the matrix that we're looking for, okay, to describe something, the image of the transformation of X with respect to basis C should be some matrix M times the coordinates of X with respect to basis B. Okay, so let me write that out. The coordinates of the image of X with respect to basis C should be a matrix M, that is way too many, M multiplied by a vector, or excuse me, multiplied by the coordinates of X with respect to basis B. Okay, so again, going from B to C here. Okay, we're looking for some matrix to make that jump, the transformation and the change of basis at the same time. So M is going to be made up of the columns, which describe each basis vector of B transformed, gone through the transformation, and then described in coordinates C. Okay, and this will achieve two things. So let me summarize. M will, 1, transform the coordinates, and 2, change the basis from B to C simultaneously. Okay, now we're going to use 3 steps, and if you're looking at the field notes, I need you to make some changes because I made a typo. So, in order to do this, we are going to do basically exactly what we did to change the basis before, with one extra step to use the transformation. So first, transform all vectors in basis B. So B1, B2, all the way up to Bn, put them through the transformation. Then 2, okay, I don't want to describe them in B coordinate vectors because I want to transform them and then change them into C. Okay, so transform them into C coordinate vectors. So this should all say C. Sorry, friends. That was what was messed up. Okay, so write transformed vectors in terms of basis C. Step 3, this is the easy part. Write vectors as columns for M. And that's it. Okay, so first, we basically do the transformation with the basis vectors, make the change of basis ourselves with those basis vectors, and those end up being our columns for that transformation matrix that will take all coordinates through the transformation and change the basis at the same time. So let's look at an example. And we start off really easy so that we aren't overwhelmed by this. So we'll have 2 bases here, D and B. They are bases for 2 distinct vector spaces. Okay, and we have a linear transformation such that when you transform D1, you get 2B1 minus 3B2. and 2d2 minus 4b1 plus 5b2. Okay, well that sounds like a very specific transformation. All right, so if we're trying to find the matrix relative to D and B, that's very directional, from the basis D to the basis B. Okay, so step one. Transform D vectors. Okay, so did I put the vectors for the basis D through the transformation? Yes, check. Step two. Okay, write transform vectors in terms of the basis B. Did I do that? Yes, I did. So you can see that T of D1 with respect to basis B described here is 2, negative 3, and T D2 with respect to basis B is here, negative 4, 5. Okay, and all that's left to do, step 3, is make those columns. So my matrix transformation that will both do the transformation and change basis from D to B is 2, negative 3, negative 4, 5. That's it. Okay, now let's simplify it down a little bit. What if we are going from the same vector space, okay? If we don't need to change the basis, okay, then we can go back to what we've learned before, okay? And this phrasing is really important. So no change of basis. Okay, all right. So if we are only dealing with one vector space and no change of basis, then the matrix M, which was here, okay, is called the matrix for T relative to B, or the B matrix for T. Okay, and that is exactly what we did before. To get our end result, the image of X written with respect to the basis B, okay, we multiply by M, we multiply the coordinates for X in terms of B by M. But those are just, that is exactly what we've done before. The matrix, the change, basically this, the transformation in terms of the new basis. Okay, so pretty simple. Now let's look at an example with polynomials. Okay, our favorite thing. All right, and here I just redid I just re-put the image again. So we are letting this transformation in this example go from polynomials of at most degree 2 to polynomials of at most degree 4. Okay, and it maps a polynomial into the polynomial p of t plus t squared times p of t. So instead of calling this p of t, let's call this like p1. And so just to get ourselves familiar with this transformation, let's find the image, which means put what is the transformation of this polynomial. So all I have to do is plug this in to this, this format. So I've got 2 minus t plus t squared plus t squared times the original polynomial. 2 minus t plus t squared. Sorry, my t's and my pluses look a little similar. So 2 minus t plus t squared plus 2t squared minus t to the third plus t to the fourth. All right, let's combine like terms. 2 minus t plus 3t squared minus t cubed plus t to the fourth. And that's my image. Okay, not so bad. Ooh, a review. Okay, I'm going to leave this one for the field notes so that these notes are not too long. Remember, in order to show something is a linear transformation, you need to show two things. Okay, one, you need to show that the transformation of a constant times a variable, in this case p of t, or excuse me, times the vector, is equal to the constant times the transformed vector. Okay, and then 2, you need to show that if you transform two things being added together, I'll call this one A of t, two vectors being added together, that's the same thing as adding their, sorry, my parentheses are horrible, transformations together. If both of those things are true, then t is linear. And to give you a heads up, t is linear in this case. Okay, now here's what we are here for today. Find the matrix T relative to this basis to this basis. Okay, so basis 1, we'll call it B, is the basis for polynomials of at most degree 2. And basis 2, we'll call C, is the basis for polynomials of at most degree 4. Okay, all right, to find the matrix relative to these bases means find the let's not get into the steps. I am looking for a matrix that will not only change the basis, but will also do the transformation we described at the beginning, which is also up here. This P of t is supposed to be over here. All right, so what did we do in step 1? 1, we transformed all of the original basis vectors. So t of 1 is 1 plus t squared. T of t is t plus t cubed. And t of t squared is t squared plus t to the 4th. Okay, so step 1, transform all the original basis vectors. Step 2, describe those transformed vectors in terms of the basis c. So t1 of c is 1 for the constant, 0 for t, 1 for t squared, 0, 0. I'm going to run out of room. T of t with respect to basis c is 0, 1, 0, 1, 0. And t of t squared with respect to basis c is 0, 0, 1, 0, 1. Okay, and then to find the matrix, which I will give myself more room to do up here. Okay, so M, all right, is just these 3 columns. So 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, and 0, 0, 1, 0, 1. So this was more of an example that went with the first set of notes, the first kind of set of things that we did, because I did, in fact, both change the basis and go through a transformation, whereas what we just talked about was not changing the basis at all. Okay, but this is another example of how to do that with polynomials. Now, I want to get into the good stuff. How do we apply this to what we've been learning about similarity? So, important things. Okay, so we first are looking at, again, a transformation being a matrix multiplied by a vector on the left. Now, if A is diagonalizable, and you learned a couple ways in 5.3 to tell whether or not A is diagonalizable, remember that should mean that A is equal to PDP inverse. Okay, 1, there is a basis B for Rn that is just the eigenvectors of A. Okay, and that makes sense because if A is diagonalizable, then it has to have n eigenvectors, which means, and if it has exactly n eigenvectors, and the eigenvectors are linearly independent, that's a linearly independent set of n vectors, which automatically makes a basis for Rn. It's connecting a few dots there, so if you need to play that again, pause and say that again. Okay, and basically, if we end up diagonalizing a matrix, we find a diagonal matrix that represents the transformation. Okay, and right, okay, so A equals PDP inverse, D is the diagonal. Okay, D, this is what we're saying. This is the most important part. D ends up being the B matrix for the transformation. Okay, so D, if I go back and looking at our notes, the B matrix for the transformation. So this is, if I can diagonalize A, I will get this matrix here, as long as I'm not changing the basis. Okay? So this, number one, a couple of notes. If you see this, remember that just means A is similar to the matrix D, which is a diagonal matrix in this case. Okay? And then what I just said was D is the matrix that it's the transformation in terms of basis B. Okay, so D is this matrix, okay, with no change of basis. We are just writing the transformation in the basis B. Okay? And if B is the basis for Rn, formed from the columns of P, the columns of P are the eigenvectors of A. Okay, so a couple important things. Okay, so let's figure out this document real quick. All right, so what if then we're just dealing with similarity? Now here is the difference. What we just said back here was that A is diagonalizable. D is a diagonal matrix. And this also applies, means A is similar to D. But what if I just know that A is similar to a matrix C? Okay, so if you want to rewrite this, this should say A is P inverse. Okay, we can still use C as the B matrix for this transformation. Okay, and we can still use a basis to form the columns, a basis of the a basis of the vector space as the columns of P. Okay, and actually this is going to work for any matrix we can say is similar to A. And so if I end up wanting, because I have, the transformation is A multiplied by X. Another way for me to describe that is multiplying, instead of doing A, me writing P inverse times X. So the first step is multiplying by P inverse, second step multiplying by C, and then ends up multiplying by P, gets me to the same place if I had just multiplied by A. Okay? Okay, so why do we want this? This is going to give us this understanding that we can represent A in kind of a factored way. Gives us the ability to say that I can represent A in a whole different, that transformation matrix, in a whole different number of ways, as long as I have a matrix that is similar to A, which I can put here, and I have a basis for the vector space I am going in. That basis is going to go in the columns of P. So here's what this says. Okay, if T is notice that these dimensions are the same. Okay, so we've got a square matrix. Okay, V is any basis for this vector space we're operating in. Then the B matrix for T is similar to A. What that means is right here. Okay, they are similar matrices. So you could either write it this way, or you've been writing it like A equals P times T B P inverse. Okay, this transformation matrix, the description of the transformation while in the basis B, okay, is this TB right here. Okay, so if I can say that any matrix that A is similar to, as long as I've got the basis vectors lined up in P, is going to be that transformation matrix. That makes describing the transformation a whole lot more flexible. Okay, so let's tackle this a little bit. Okay, let's do a couple example problems. All right, so example 3. We're going to find the B matrix, okay, for this transformation. So finding a description of the transformation in the basis B. That's a good way to say it. Okay, I've got a basis here, these two vectors, and this is my actual transformation matrix. Now, knowing these pieces of information and knowing that A is going to be similar to any B matrix for this transformation, I have that the transformation in the basis B is going to be equal to P inverse AP. And the reason this is really nice is because I already have A, and I can use any basis vectors for the vector space to make the columns of P. So I can put an A in the middle. Maybe I'll give myself a little room for P inverse. Okay, so I'll put an A, -1, -2, 4, 4, 3. I put in P, which is made up of the columns, or these basis vectors. 3, 2, -1, 1. Okay, and now P inverse. Well, I got to do a little inverse here. So I see that the determinant is 3 plus 2, so it's going to be 1/5. And then I've got to do some switching and negating. Okay, and so multiplying all of these things together will give me the transformation matrix in the basis B. That was super easy. I didn't have to find the original basis vectors. I didn't even have to know, I didn't have to put them, I didn't have to change the basis. This is a lot simpler, given very basic information and actually very flexible information, because I could have done a different basis and gotten another matrix that would have done this. All right, so this, when I multiply it all out, we'll skip to the good part, is -1, -2. So actually, I don't know that this is right because I know that I messed it up on my field notes. I think I have an extra negative here. So check this for me, okay? But we're running to the end of the video here, so I want to make sure that I give enough time. Now let's see, did I give myself space? I did not. Hooray. Okay, so the last one I'm going to do is example 4. I'll leave example 5, which is actually example 6 in the field notes. What a crisis. But this one is a little bit long, so I want to make sure we do this together, or at least go step by step. So I've got a transformation going from R2 to R2. I want to find a basis B. Okay, so now instead of looking for the actual transformation matrix, I'm looking for the basis, with the property that this transformation matrix is diagonal. So that tells me that this transformation matrix is going to be the same as D, considering that A is going to be P, TB, P inverse. And since this is diagonal, this is really going to be P, D, P inverse, which should set off some alarm bells for those of you who just came from the rest of chapter 5. Okay, here is A, and I want to find this basis specifically for under these conditions. If you're looking at this and saying, wow, that looks like I need to diagonalize A, you are exactly right. I need to find the eigenvectors for A. Now, I need to find the eigenvectors. I don't need to actually go through the whole process of diagonalizing because I just am looking for a basis. And the eigenvectors will give me a basis for R2. Because I should, if this is a diagonalizable matrix, which this is kind of given a condition, it is going to give us 2 linearly independent vectors, which should automatically form a basis for R2. So, to diagonalize the matrix, or just to find the eigenvectors, A minus lambda I. Okay, so I've got 5 minus lambda, -7, -3, 1 minus lambda. Okay, all right, finding the determinant. I've got 5 minus lambda times 1 minus lambda. 3 negatives make this -21. So that makes this 5 minus 6 lambda plus lambda squared minus 21. Got some factoring time. Okay, this is going to be minus 16. All right, so I got 8 and 2. Lambda minus 8. Lambda plus 2. So I have 2 eigenvectors, and they are lambda equals 8 and lambda equals -2. So when I plug in lambda equals 8 into my original A minus lambda I matrix, I am getting -3, -7, -3, -7, and that is right. I want to get something linearly dependent. row reduce, I'm getting the matrix 1, 0, 1, 0. Okay, that tells me that x1 is equal to negative x2. Okay, so the eigenvector I'm getting here is negative 1, 1. Okay, if I do the same thing, maybe I'll pick a different color. For lambda equals negative 2, the matrix I'm getting is 7, negative 3, 3. Also linearly dependent. When I row reduce, I am getting 1, 0, negative 3 sevenths, 0. So that's going to give me a fraction. It's going to give me that x1 equals 3 sevenths x2. If I choose x2 to be 7, that makes x1 3. And there is my other eigenvector. Okay, so maybe I'll write the basis because I'm unintelligent and forgot. So the basis, b, is going to be equal to the two vectors, negative 1, 1, and 3, 7. And there we go. Okay, all we needed to do was find the eigenvectors. So kind of all tying all of this together. I'm going to leave example 6 for you to do on your own. Okay, practice. The one thing I want to give you a hint for is that if I want to find the B matrix for this transformation, again, this is describing a transformation matrix that does not change bases. So I'm looking for a transformation that stays in basis B. So this transformation A, but described in terms of basis B. Notice one thing. This is different from the last example we just did because it doesn't have to be diagonal. We don't have to use the eigenvectors of A. We can just use any basis vectors to make P. Okay? So you are looking for, again, the transformation with respect to B, which will be P inverse AP. Okay? And you can use this basis as the vectors that go in P. And using A, and then use your calculator, or if you're having practice, row reduced to find P inverse. Okay? All right. And that should be easy enough. So recap, what did we do today? We reviewed three things, all the way at the beginning here. What we did was we reviewed transformations. Okay, what did that look like? Going from one vector space to another vector space. We also reviewed change of basis. And we looked at how do I make a matrix that does both at the same time. In order to do both at the same time, we use the original basis vectors and we transform those. Then we write those vectors in terms of the basis we're looking to go to. Those will end up being the columns for that matrix. Quick 3-step process. Okay. And then we looked at what if we just want to describe the transformation in terms of the basis. Okay, because this would be A, but if I need to describe A in terms of the basis B, how do I do that? Okay, and the reason that was so easy to find was we were able to use what we've been talking about for the last couple days with eigenvectors and eigenvalues and describe that as a diagonal or a similar matrix transformation, meaning there are many ways that we can describe A in terms of A as the transformation, but instead of in terms of the standard basis, now we want to write it in terms of B. So we said that D, this diagonal matrix, could be T sub B, okay, if we knew that it was diagonalizable, but it could also be C. The only difference is what we put in the columns of P. If we are using a diagonal matrix as this B matrix, we end up putting the eigenvectors in P. If we use just a non-diagonal matrix as the B matrix, we just put basis vectors in P, and those basis vectors can come from anywhere. Okay, all right. I know this was a difficult lesson. If you got this far, I know that there are probably questions, so I will definitely be trying to do some examples in class and in office hours. Feel free, if you are working on other things, to text me or send me an email if you have questions.